Classical theory of NMR signal. As we have seen in basic concepts of NMR signal, that when we apply the external magnetic field, the degeneracy in the nuclear spin energy level will get break. So those of which are opposing the external magnetic field, they will go to the higher energy level, and those of which are overlapping the external magnetic field, then they will go to the lower energy level. There creates a population difference that will be given by delta E. Delta E that will be proportional to the external magnetic field, and the delta E, that is energy level, the difference in the energy level will be proportional to the population difference, and that creates a relation. The external magnetic field strength, that is B naught, will be proportional to the population difference, which gives this relation that delta E will be proportional to B naught will be proportional to population difference. Now as we can see here, that the difference in energy level due to application of the external magnetic field creates a population difference, and the excess of population will be there in case of the lower energy level. Let's say we have 6 extra spins left than that of the higher energy level. So all these 6 extra spins will be aligned in some direction where the external magnetic field is applied. Let's say the external magnetic field is applied to the Z direction. Then all this spin will be aligned to the Z direction. So the external magnetic field and all these extra spins that is aligned to the similar direction to that of the external magnetic field will generate a magnetic field that will be along the Z axis, that is known as Z magnetization or G magnetization. Let us understand this with the figure. This is X coordinate, Y coordinate and the Z coordinate. All these 6 spins are aligned to the Z axis, that is given as like this, which is denoted by the thick line over here. Now all these spins are aligned to the Z direction. As soon as we apply the radio frequency, let's say we have applied the radio frequency from the Y direction. So the radio frequency will be applied in the form of pulse. The radio frequency pulse will applied. Those spins which are aligned to the Z axis will now rotate towards the X direction, that is X axis. Since the detector is placed in the X axis, as soon as this spins reaches, or the magnetization will reaches to the X axis via XY plane and gives an NMR signal. Here we can see the different kinds of NMR signal. Like at 45 degree, there is less intense than that of the 90 degree, and in case of 180 degree it will get vanished, and in 270 it is opposite to that of the 90 degree. Similarly, these all are the radio frequency at the different rotational angle. So if we control the radio frequency in such a way that at 90 degree all this magnetization will align towards the x-axis, and we will get the intense signal. So with the control pulse we can achieve an intense signal. To understand this 90 degree pulse in better way, we can consider this figure. Here x-axis, y-axis and z-axis. Z magnetization is there, the radio frequency pulse will be coming from the y-axis and it will hit the Z magnetization. As soon as this Z magnetization will rotate and reaches to the x-axis like this, we'll get the NMR signal since we have the detector placed in the x direction. Now we can imagine that the radio frequency will be coming from the y-axis with this in pulse form. Once this pulse hits this Z magnetization, then it will rotate to the x-axis, we'll get the NMR signal. Again there will be a pulse interval. There the relaxation process will occur. So during this relaxation process, this all relaxation happens and again the magnetization will move towards the Z axis. Again this process will happen since the radio frequency is coming from the x direction, y direction, then again it will go back to the x axis, we'll get the NMR signal. Like this the whole process will continuously be repeating and we'll get the intense NMR signal. Here we can understand the relaxation process in better way, that once the pulse interval occurs, the relaxation process will be there. The relaxation process, in which two kinds of relaxation process will be there. One is transverse relaxation, another is longitudinal relaxation process. In this, the relaxation process during transverse will be like all those which are aligned to the x-axis here will be distributed to the x and y plane in a equal manner, in such a way that all around this x y plane the spins are distributed and it will get relaxed. That time of relaxation is given by T2, and again another pulse will come back. So in the span of getting back of another pulse, we will get to see the magnetization distributed themselves equally in the direction of x and z direction. Since the pulse is coming from the y direction, so both of them will get distributed to the x and z direction equally, and again it will go back to the z direction. So whole this process is called the relaxation time. In this, the pulse time will be in the millisecond, and it can be calculated with the magnetic field associated with the radio frequency V1. Here we can see the rotational frequency from z-axis to x-axis will be given by the radio frequency B1, that is the rotational frequency will be equal to B1 into gamma of the proton, that is gyrometric ratio of the proton. So we can write in the short form as RF is equals to B1 gamma H. This rotational frequency is the frequency that is associated with the field strength which is applied externally. Pulse time can be calculated using the magnetic field associated with the radio frequency, that is B1, the rotational frequency of Z magnetization. As we have seen above, that to align Z magnetization towards the x-axis for NMR signal, we have used the radio frequency in a pulse form like this. So the pulse time for 360 degree equals to 1 by rotational frequency. Now if we want to find out the pulse time for 90 degree, then we need to divide this by 4. If we divide here by 4, then we need to divide this whole equation by 4. We'll get the pulse time for 90 degree equals to 1 by 4 into RF, that is rotational frequency of jet magnetization. Using this, we can solve the problems as in an NMR spectrometer containing a 2.5 Tesla magnet, Larmor precessional frequency of proton is 100 MHz. The radio frequency used in this spectrometer has an associated magnetic field strength, that is 2.5 into 10 to the power minus 4 Tesla. We are asked to find out the duration of 90 degree pulse in this instrument. Let us see how we can approach this question. Since we know that pulse time for 90 degree is equals to 1 by 4 into RF. Now here in this equation, if we find out the value of RF, then we can easily find out the pulse time for 90 degree. Since we know that RF is equals to B1 into gamma h is the gyrometric ratio for the proton, that is 42.57 megahertz per Tesla. So we can write this as gamma into B1. So just substituting the value what we have, 42.57 into megahertz per Tesla into 2.5 into 10 to the power minus 4, that is the value of B1 which is given in the question, that is 2.5 into 10 to the power minus 4 Tesla. We will get RF is equals to 106.425 into 10 to the power minus 4 megahertz. If we convert this megahertz to hertz, then we will get radio frequency equals to 10642.5 hertz. Since we know that 1 megahertz is equals to 10 to the power 6 megahertz, 1 megahertz is equals to 10 to the power 6 hertz, then we can just multiply this by 10 to the power 6, will get to have 10642.5 hertz. So the duration of 90 degree pulse we can get by just putting the value of RF in this equation. We'll get it as duration of 90 degree pulse is equals to 1 by 4 into 10642.5 hertz. This hertz we can write it as per second. So it is in the denominator per second. Then if it goes above, then we'll get second. So the value we will get it as 23.5 into 10 to the power 6 second. Let us match our answer with the question's option given above. Here option A, 25 into 10 to the power minus 6 second. It is near about what we got in our answer. B, we have 50 into 10 to the power 6. This option, it cannot be the answer. Option C, 25 into 10 to the power minus 5 second. Here this is near about our numerical value, but this is 10 to the power minus 5, which is not possible for our answer. D, 50, this is also not possible. So approximately for more appropriate value, we can give answer A as a right answer. With this, if you like my videos, I want you to give thumbs up right down below. Thank you.